second keynote speaker of the conference, Ryan Abernathey, who is associate professor and leader of the Ocean Transport Group in the Columbia University Department of Earth and Environmental Science, and also co-founder and a community leader of the Pangeo project, as well as the CEO of Earthmover. And we're quite excited to hear about his thoughts on the future of Earth system data infrastructure this morning. So thanks, Ryan, and the floor is yours.
Okay, great. Okay, here we go. Fantastic. Well, first, thank you so much for the invitation. It's wonderful to be here, connect with so many colleagues I haven't seen in many years, and meet many faces I've only seen on the internet. So thank you for all waking up early to come to a talk about data infrastructure. Why should you care about data infrastructure? Why not just sleep in? Show of hands, who here is personally concerned about climate change as a problem for humanity? Something we can almost all agree on these days, right? Climate change, adaptation, and mitigation are really going to require us to harness data in new and innovative ways, right? We have to go far beyond just using data for research and really build operational production-grade systems that can leverage data in real time to understand and, in many cases, even intervene in the Earth system. And this change is happening today, right? So I live in New York City. Climate Week took place over a month ago. I participated in an event called Climate Data for the Financial Sector. There are a bunch of people from all the big banks, Goldman Sachs and Deutsche Bank, and all of these bankers were trying to figure out how to respond to all of the new regulatory pressure, all of the new rules, and all of the new economic factors around climate. And the number one thing they were asking for was more transparent, reproducible climate information. And that connects directly to the second reason why I think you should care about data infrastructure, which is open science. So open science is this broad revolution that's currently taking place in how we practice science. So rather than hiding all our code, all our data, and all our methodology behind a curtain, we're now beginning to share everything openly, allowing other people to easily extend and verify our results. And I think this is an enormous development for science in general. It's going to help us all move faster, even as it is somewhat threatening to certain status quos. And a big part of this open science is inclusion. Right? We know that there's many people who today are excluded from the scientific process. And these two issues come together when we look at people in the developing world. We know people in the developing world and impoverished countries are going to be some of the most impacted by climate change. And so it's crucial that they can participate in climate science, in Earth system science, in the research and in the applications. And so, as I'm going to try to argue, both of these goals really depend on how we build our data infrastructure. And we have the opportunity to build the next generation of data infrastructure that will really enable us to be much more effective on both of these fronts. Okay, so that's what my talk is about. Who am I and why should you listen to me? Okay, what right do I have to say anything on this? So, as Stephanie mentioned, I think I can bring a unique perspective to this question. And in this talk, I'll wear a couple different hats, right? So I can wear the hat of a scientist. I'm an oceanographer by training. I study ocean turbulence and ocean circulation. And I've been involved in NASA-sponsored research for many years. Over the years, I've sort of become more and more interested in software and software development. So I'll spend a lot of time talking about the Pangeo project. I'm a core developer of certain widely used Python libraries such as Xarray and Zarr, and so I've learned a lot from that experience. And finally, most recently, we started a company called Earthmover, where we're trying to really build some of what we see as the key missing components of data infrastructure. So towards the end of the talk, I'll put on that hat as an entrepreneur and try and explain what we are building and why we think it's necessary. So I'm organizing my talk as a sort of personal history of my experience with data infrastructure, right? And I've divided the timeline roughly into 3 components. The past, which I'm very arbitrarily declaring ended in 2013, the present era, which basically comes up to today, and then the future. And I want to say that this is a very personal and subjective view on this problem. I'm not trying to be comprehensive. I couldn't possibly review every technology and every approach. These are the tools and technologies I've been exposed to and that I've worked with over my career. So let's go into the past, right? I'm going to tell you about the way of working with data that I was trained on as a graduate student. So this is me as a grad student in 2008. And I was shown by my mentors and the more senior people in the lab how we work with data. You start with your personal computer. You get some data on that computer, you do some analysis, and in those days it was MATLAB. If you need a little bit more resources, maybe there's a server that you can go use, shared with other people. If you need more, you can upgrade. There's some cluster somewhere at the university that you can use. And if it gets really big and you're lucky, you can get access to a national scale supercomputer. So what does this sort of data infrastructure really provide? What are the sort of building blocks that you can rely on in this style of infrastructure? Well, you know, there's going to be some kind of Unix operating system. There's some files. You can store files on the server. You can run your favorite programming language. And you can access the system through a terminal. That's about it. That's all that you're guaranteed. Now, they may be very powerful systems, but that's what the infrastructure really looks like. Many of these systems aren't even connected to the internet when you get to the HPC level. You can't even connect to the internet. The use of high-level databases, services, API, completely unknown. And there's really no user experience, no user interface beyond that terminal in most of this. And so that's pretty limiting. But on the other hand, it's fine. That's what these systems are good at what they were designed for, which is really fundamentally simulation, right? So I want to really sort of clarify what I think is this important difference between simulation and data-intensive science. So I'm an ocean modeler, so I've done a lot of simulation. And what simulation does is it basically starts from a very small amount of information, like just some equations or some numerical code, and it runs that through a computer, even a supercomputer, and turns it into a massive volume of data. You can generate simulations of petabyte scale, which I'll talk about. And now you've got a bunch of data sitting on the computer. Data-intensive science is kind of the reverse process. Taking all of that data and boiling it down into some actual insights, some understanding, some predictions that we can use to drive action or decision making, or just learn something about the Earth, right? And these are really different types of workflows, right? So simulation, for the most part, is a pretty constrained computational problem that's well understood. So if you're doing Earth system simulation, you're probably solving some fluid equations, Navier-Stokes equations or something like that. And there's certainly innovation to be made there, but we basically know how to do that well. We've been doing that problem for 60 years on computers. We have a very optimized architecture and software for doing simulation. And these type of systems are really built to do it well, and they do a great job. But data-intensive science is completely open-ended. It could mean anything. It's very interactive. The human is in the loop for data-intensive science, looking at the results, trying to understand what they mean, trying different methods. This is, of course, is where so much AI and ML work is today, to actually find what is the right architecture, what is the right algorithm. And so it's very hard to design a system that is optimized for that. And there's really no standard platform. So when we go to do data-intensive science on these type of systems, we end up following this sort of anti-pattern that actually my colleague Shel Gentleman coined this term. We create data fortresses, okay? So let me explain what I mean by that. So this building here represents my very privileged university, Columbia University in New York. And what we do is we put a big supercomputer in our basement, and then we pay students and postdocs to spend their time downloading data into our system, right? So who has spent their time downloading data onto a big computer here? Raise your hand. Okay, yeah, so that's the students and postdocs who raised their hand probably. You know, we really use this relatively cheap labor to just run these data pipelines in a very manual way. That's the pattern I observe, right? And we can do this because that labor is cheap and we're pretty well funded. And now we have a data fortress. We have all this data in our system and it becomes a strategic advantage for us. And we can do science that other people can't do because we have all this data. And that's maybe good. That allows us to do some cool science. On the other hand, when you start thinking about the open science aspects, you can see what a barrier it becomes. So who has ever gotten some code from a colleague, and the first line of the code is something like this: open up terabytes of data that you don't have, right? These data fortresses are a huge barrier to collaboration, right? And so here's my sort of critique of this traditional infrastructure. This emphasis on files really creates a lot of work, moving around and organizing all of these files. And this is how our students and postdocs are spending their day, just munging around files. And of course, those same data sets get duplicated over and over again at many different institutions. So how many people here are sitting on 10 terabytes of Era 5 data on their own computers, right? That's rarely collaborative work. It's done in isolation. It's not shareable. It's very expensive to work this way. You need, expensive local infrastructure like a big computer, or you need access to a big university or national supercomputer. And that really limits who can do this type of science and who can be part of the scientific process. These systems are highly secured. Access is limited to credentialed members of the institution. And that's a feature, not a bug, but it's really the antithesis of collaboration, right? And if I want to give access to one of my colleagues to my fortress, that's extremely hard. Finally, I find these systems are very much specialized, actually, and code you develop in one can be very hard to run in another. So that's what I call the past era. And now let's move to the present, right, which I characterize as an era of explosion of big data and new technology. So for me, the present era began when I first saw this data. I had a very nice movie here, but they made me convert my slides to PDF. So just imagine how beautiful this movie would be with all of these eddies and waves moving around. So I'm a physical oceanographer, and I study how ocean turbulence affects the global scale ocean circulation and ecosystems, right? And simulations like this are absolutely transformative for our work. They really allow us to resolve fundamental length scales that before were not resolved, that result in much more realistic ocean simulations. And so this is where we need to go in the field of ocean modeling. And the basic geometry of this problem sort of requires that when you run ocean models at this, with these characteristics, they're going to produce petabytes of data. And so petabytes is where the old infrastructure approach really breaks down. I mean, just about nobody can really download petabytes of data. It's just too slow. You don't have enough hard drive space. It's not going to work. And furthermore, if you're going to download it, I mean, what, is everyone then going to download it? It just doesn't make sense. So this trend is far from unique to oceanography. As we all know, data volumes across every field of Earth system science are exploding, from land, atmosphere, ocean. Here's 2 graphs I found from NOAA and NASA. I tried to find one for the Copernicus program and failed, but I'm sure it's out there, right? And they all look the same. And so in this landscape, it's pretty clear to everyone that we need to bring the compute to the data, not the other way around. But how exactly should we do that? So I think the modern era, the present era, was very much kicked off by Google Earth Engine. So another survey. Who here has used Google Earth Engine? Yeah, a lot of people, right? It's a great tool. Google Earth Engine sort of opened people's eyes to what's possible with cloud-style computing. Right? So rather than downloading all the data to your own machines, you can go to this platform, do full end-to-end workflows, have a pretty good user experience, get access to massive data sets and massive compute, all through, basically through a web browser. And Earth Engine remains one of the most powerful and influential tools in the Earth observation space. But of course, not everyone wants to outsource all of our data processing to Google for many different reasons. It's just not practical. There may be political or economic reasons why that's not desirable. And in general, Earth Engine is not really an open platform. It's controlled by one company. So since Earth Engine launched, there's been a huge amount of effort to try to recreate parts of this type of experience in a more open, modular, flexible way using open source and open standards. And I'm going to tell you about our work in this direction as part of the Pangeo project. So what is Pangeo? So you've perhaps heard the word Pangeo at this conference a lot. Many of you are perhaps collaborators in Pangeo. So Pangeo emerged from a group of scientists who were also working on software, specifically folks who were working on the Xarray Python package. So in 2017, we got together for a meeting at Columbia University, and we formed this Pangeo collaboration. And Pangeo is a grassroots project. It was formed without funding, without agency support, without institutional support. It's just people coming together to work together. And the mission of Pangeo is really to advance the technology used for data-intensive Earth system science. Later today, and for you is going to have a talk on Pangeo within the European Open Science Cloud, and I think there's plenty of opportunities at this conference to learn more. There's really 3 core aspects to Pangeo: the community, the software, and the infrastructure. And so this community is open to anyone. We've been holding a weekly meeting for the past 6 years online, and we have a pretty active discussion forum, online resources. In terms of software, there's no software called Pangeo. Instead, what we do is we work on open source scientific Python tools, trying to improve their integration, make sure they're working together to meet the needs of Earth system scientists. And finally, we've worked with infrastructure providers and gotten involved in infrastructure ourselves to deploy these tools in a way that they're scalable and effective and that scientists can actually use them. And I think the most important aspect of what we've done in the Pangeo project is to create this feedback loop where the needs of scientists are really directly communicated to the people developing the software, people deploying the infrastructure. And this is actually pretty rare in the way we do scientific software, or at least it was rare. It's becoming more common. And I think this sort of feedback loop is really the key to any successful software, any successful system, is to actually be constantly incorporating the needs and of the end users. And in terms of deployment, the Pangeo software has been run in many, many different computing environments. From your own, you can just run it on your laptop. It's been deployed in all kinds of HPC contexts and in all of the major clouds and cloud-like systems. So who are these collaborators? Well, this is my most recent logo soup. I've been informed I'm leaving many people out here. But the point is, Pangeo is a completely open project. Anyone can come and start contributing and working together with this community. From the beginning, it's been a collaboration between scientists in Europe and the US. So at our very first meeting in 2017, we had a European contingent, folks from both France and UK, coming over, taking part in the process. And today, you can see a wide range of different universities, agencies, and increasingly private companies who are participating in this. And I think the presence of the private sector is really important. That's where there's a lot of technological innovation happening. And so we work closely with folks from Microsoft, Google, NVIDIA, and many smaller companies and startups on this technology. So what exactly is Pangeo? How does it work? Well, here's a very simple diagram that explains what is this architecture that we've advanced. And the point here is that simple equals scalable, right? So in Pangeo, we've developed a sort of architecture where a user connects to a system remotely, usually using a Jupyter notebook type interface. In that system, they're running their compute processes. And they're using a tool like Xarray to query and analyze and visualize data. And that tool is connected to a shared storage system. In the cloud, this is very often something like cloud object storage, where data can be accessed in analysis-ready, cloud-optimized form. And this really simple architecture allows you to move compute to data in a very flexible and cheap and simple way, right? And when there's a need to scale up that analysis and process terabytes or petabytes of data, this framework can be integrated with different ways to scale out that are sort of quite generic and not specific to one sort of system or architecture. So tools like Dask or Apache Beam are used widely in this community to, scale out data processing to hit that petabyte scale. And the key property here is if you're just connecting directly to data in efficient cloud object storage, it's very scalable. You can process data really quickly using this type of architecture. And so this is kind of what Pangeo people are doing, and you'll see more from Anne about this in a later talk. So Pangeo has become pretty widely adopted. It's used by both individual scientists to get their work done, and it's also used increasingly by large institutions as part of other systems and other infrastructure. And we've seen that at quite a few talks today. I think Pangeo has also had a big impact on the open science movement. Right? So here's a project I'm particularly proud of. We partnered with the Coastal Ocean Environment Summer School in Nigeria and Ghana for the past 2 years. And this is a group of oceanographers in Africa who don't have a lot of access to computing infrastructure, but are very eager to work with the latest data and models. And in this partnership, we provided this cloud infrastructure, allowing these scientists to connect directly to cloud-based computing environments and data. And so this is a great prototype of how this type of infrastructure approach can really be used to make science more inclusive and bring more people into the scientific process. So to wrap up this section of the talk, here's sort of my assessment of what have been the main successes, but also the limitations of Pangeo. So it's great that these tools have been widely adopted. That's very satisfying to me as someone who's worked on this. And in the process, we've empowered thousands of scientists, teams, and companies to be more productive in their data science work. I think we've demonstrated that this bottom-up, user-driven, open-source approach can generate great tools that people really like to use. And we've pioneered this sort of cloud-native style data infrastructure that's not reliant on a big national supercomputer in order to scale up. In terms of the limitations, this Pangeo stack remains hard to operate. The technology is inaccessible to many people because it requires quite a bit of expertise in some cases to stand up all the different components. And so deploying and operating this infrastructure requires experts, people who understand cloud computing, and there aren't a lot of those people around in our community. They're expensive to hire, and this really limits the scale that Pangeo can achieve. We've prototyped this pattern of creating these hubs, Jupyter environments that you can work with in the cloud. But sometimes I worry that though we're just creating more and more silos as each institution creates their own distinct and unconnected hub. So that's a potential limitation. And finally, getting data into the cloud is a huge source of toil. If you ask the Earth Engine folks where they spend most of their efforts, they'll tell you the same. It's on building those data pipelines to extract the data from wherever it originates and ingest it into their system. And the same is true for Pangeo or any other sort of cloud-native approach. So what have we learned from Pangeo? What are the trends happening today? Where are things headed? I'm predicting that within a year or two, this conference may be renamed the Big Data and AI from Space Conference, right? We can clearly see this trend where AI is influencing more and more of science, and it's becoming more and more important tool. And of course, it's actually a natural extension of our focus on big data, because AI is really able to leverage that data and do very cool things with it. So these trends, the three main trends I see is that the private sector is going to play an increasingly important role in our system science. Second trend is what I call everything, everywhere, all at once. More and more applications are going to want to access all of the data, not just some little piece, not some area of interest, the entire data set. And finally, we're going to see that everyone is capable of becoming a data provider and sharing planetary scale data with the world. And so in response to these trends, I'm going to make sort of two recommendations about how we should think about building infrastructure going forward. So first, perhaps obvious to you, perhaps not, but Earth system data are really not just for academic research anymore, right? And this has always been the case, for Earth imagery, but increasingly in climate, there's a huge amount of investment going into what we would call climate tech, and a huge number of existing and new companies that are moving into working on both climate mitigation, so reducing the greenhouse effect through various interventions, mostly on clean energy and carbon removal, and then also working on climate adaptation, understanding of climate risk and building systems that allow us to adapt our society to it. And a huge amount of the solutions are going to come from the private sector. So as data infrastructure people, we really need to think about how to accommodate the growing needs of the private sector. And if the data infrastructure that public institutions are building doesn't meet their needs, they're just going to rebuild it in the private sector. And it would be much better if we could collaborate. The second trend is everything, everywhere, all at once, right? So training next generation Earth system AI models really requires planetary scale data sets. So what's the hottest AI out there today? ChatGPT, right? It's a transformer-based architecture. It's what we call a foundation model. A simple model, or not a simple, but a very complex model that can be trained on a huge volume of unlabeled data. Just the appetite for data from this type of architecture is vast. And we're seeing foundation models now starting to be deployed for the Earth system. And the key characteristic of these foundation models is that they just need to see all of the data. The more data they can get, the more effective they can be. So I had a chat with the creators of this ClimaX foundation model from Microsoft a few weeks back, and they told me the main constraint that they found in developing this model was their ability to get training data and organize it in a way that was computationally efficient to feed into the model, right? So we're going to see more and more of this. Companies, teams who just want all of the data from an entire archive, right? And that's not how most of our data distribution systems were designed. They're much more focused on, okay, you have an area of interest, you have a point of interest, I'll help you extract that, maybe look at a map. But this is a completely different beast. Then the final trend is that everyone can become a data provider. So Today, anyone can create valuable planetary scale data. A great example of this is this tiny company called Zeus AI, a 2-person startup based in Boston in the US. And they're really bright people, and they figured out how to use AI together with satellite data and weather data to create a really great high-resolution satellite-informed forecast product. And they want to put that out there, and they're trying to get that out to their customers. So this 2-person startup is creating a data product that is playing in the same field with big national agencies. And they need data infrastructure that's going to support this desire to share data with the world. Right? And I think we're going to see more and more of this. Any team, any group can produce a useful planetary scale data set, not just a few large agencies. So how are we going to support that? Right? So I see I'm just about out of time, so I'm going to take 2 more minutes and try and finish my talk, and then we can get into questions. So the main message that I want to convey is we really need to be building cloud-native data lakes, okay? And by cloud-native, I don't mean you have to use Amazon's cloud or any particular vendor. You can build your own cloud as long as it is fully interoperable and connected with the global internet, right? So what cloud-native data lakes are data systems that rely and build on a universal storage layer called cloud object storage. So technologies like AWS S3, Google Cloud Storage, every cloud provider and every on-premises cloud has something like this. And when we place our data on these sort of systems in cloud-optimized formats, we can share it with the world super high throughput over vanilla HTTP connections. It's simple and extremely scalable, right? So these cloud-optimized formats allow you to access data over just a standard HTTP connection. And the formats don't require you to download all the data in order to see what's inside or to subset. So examples of this are Zarr, cloud-optimized GeoTIFF, Parquet. And even if you want to build a more sophisticated data system or portal, these remain an excellent foundation for anything you would want to layer on top of that. APIs, visualization, et cetera. And they enable this really high throughput sharing of data, which anyone can both share data and access data at a planetary scale. So the technology that I have worked on is something called Zarr. Zarr is a great fit for AI-ready data when you're dealing with these sort of planetary scale harmonized data cubes. For the sake of time, I'm not going to read through this whole list. I'm going to try and move to wrapping up here. But if you're interested in learning more about Zarr, we have a Birds of a Feather session today at 1 p.m. to tell you all about the format. Okay, so this is the end. I promise I'm wrapping up. So the final slide here is that I've gone around and taken some photos of all of the different architecture diagrams that I've seen on the posters and at various talks here, right? And I've tried to pick on everyone equally. I think we're all doing the same thing. What we see everywhere we talk to is something that I think of as architecture soup, right? Every institution that is trying to build data infrastructure is building the same types of components over and over again. And this is important because this makes it a lot more expensive to scale and democratize access to data infrastructure, right? And so I think in order for us to really embrace this sort of next wave of data infrastructure, we need to start standardizing around a few common infrastructure components that we can reuse in a more modular way. And in the cloud, we have the option to procure these type of infrastructure components as a service, right? So for example, if your organization needs a Jupyter hub in the cloud, you can pay engineers to build and deploy and run that for you, or you can get it from this organization, 2I2C, the International Interactive Computing Collaboration, who provides Jupyter Hub as a service. If you want to run Dask at scale, your team can build and operate Dask clusters and run those and pay engineers to do that, or you can get Dask as a service from this company called Coiled. And this brings me finally to our own efforts in this space. If you're building a Zarr-based data lake as a service, we would like to help you do that by providing some certain key infrastructure components based on what we've learned developing these technologies over the past 5 years. And I think that these patterns are really going to help us scale up and build technology much more quickly and make that technology more accessible to more people. And for the sake of time, I'm going to skip through all of our description about what we're actually building. And I'd be happy to tell you about it offline, but I'm out of time. So I'd like to just sort of conclude with what my vision is and what my take-home message is, right? So in order to really realize these goals of broader participation, democratization of access to data infrastructure, we need to be thinking about building a federated, extensible, global data infrastructure with less sort of unique data fortresses and data silos and more of an interconnected global system that allows us to access any data set from anywhere. There's two key ways that I think we can be doing that. One is to embrace this cloud-native geospatial approach to sharing data over commodity object storage in cloud-native geospatial formats. It's a very simple thing we can do that will absolutely transform how data are shared. And then in terms of how to actually scale and democratize data infrastructure, I really think we need to start thinking about providing these system components rather than building everything from scratch, to start procuring different elements of our infrastructure as a service and let the market help to provide those services the way they do in many other areas of cloud data infrastructure. So I'm going to stop there. I've already gone way over time, and I thank you for your patience. I'm really excited to be here. I'm here to connect and discuss, so please reach out, and I look forward to talking to folks later in the day. Thank you.
So thank you, Ryan. We have time for 1 or 2 questions. So are there any questions from the audience?
Thanks, Ryan. Really amazing. One question. I mean, in your last slide, you basically started to get a little bit to the point. Yeah, how do we prevent the data fortresses on the ground to become data fortresses in the cloud? This is the development that I currently see, and to which I think there is only one way around to convince people that federation is better than isolation. But what is the key argument for that? On political, on economic, on all these levels that are important to decision makers, how do we convince them to support such an approach, including the industry, including the public endeavors?
Yeah, that's a great question, and I'm glad I finally got to the point on the very last slide of the long talk. At least I got there. I agree. This is probably the most important slide, and I rushed into it. We can look at the internet itself, right? When the internet was first being born, there was a strong desire for specific companies, institutions to sort of own the components of the internet and make it a sort of private, very sort of non-standardized service. And the key to overcoming that was all of the standards bodies that emerged to define the protocols through which we would interact, and that made the internet, with, I think, pretty good success, a pretty democratic and open and extensible network. And so what I'm showing here is just the internet, right? Like the cloud at some level is just the internet. It means connectivity between data systems, and it means standard protocols to exchange information. How do we encourage people to build something like this? Well, I believe that this is what the private sector is already sort of starting to build in commercial cloud, right? These trends are happening no matter what. It's clearly the most cost-effective way to scale planetary scale computing. And the only question is whether public sector institutions want to contribute to being part of this, or whether they're comfortable having a sort of mirror of all of the data that's going to be created outside of their control. And I really think it's better if we can actually have one global interconnected system rather than these sort of private data centers and that are then going to be mirrored by people who wish to make the data operational. So I don't have enough experience with politics to know how to make that happen, but from a sort of technology point of view, it's clearly the best state for us to be moving towards.
Francesco Sgaramella from ISA. So thank you very much for this very nice presentation. But anyway, I have one question because I have not seen the concept of moving, let's say, processing hot assets from one, let's say, side to the other. And this can, I think, help a bit the overall infrastructure. But I mean, I would like to understand from you if this is also an option that you consider, or if it was already there, I did not see it.
You're talking about like processing, like the processing chains for like different satellite data products.
Yes, for example, if you think about platform exploitation that we have, normally you can also upload processing assets to perform some computational there. So in this way you move software where the data are, and then you don't need to exchange the data, but only to exchange the results.
Yeah, so you've described what, that's how I would characterize how Earth Engine works, for example. You bring your code and all of your computing. And I think the key difference there is that there's always going to be limitations on how much compute one organization can support. And so you say I can upload my code to your system and you'll run it for me. But surely there's some limit on your budget, right? What if I want to reprocess all of your data every day? Right? You'll say, well, no, I didn't mean that. I meant something else. Whereas if this type of complete separation of storage and compute, I can just bring my own processing directly to bear on your data, and you don't have to worry about it. So, there are different use cases. I think when we're thinking about supporting communities that don't have resources, for example, the summer school I described, that's a great pattern, right? That allows one institution to host computing for someone else. But in order to support, for example, that foundation model training, it's never going to work through the way you described. So I think both are possible, but this type of architecture can support that way of working, whereas the reverse is not true. So I think this is a good foundation, and then we can layer many other services on top of that foundation, like the ones you described.
Thank you.
So thank you very much again, Ryan. And for more questions, we heard there's a BOF at 1 o'clock.
Yeah, great.
So thank you.